much. Thank you to the organizers for letting me be here virtually. Hopefully next time in person. So maybe should make this full screen. I'd like to introduce a new type of graph complex. Okay, so what I need to tell you is what type of graphs will we consider? What space do we associate to each graph? How they're glued together via differential. And then finally, what does it compute and why? But I don't want it to be a surprise. Okay, so it will compute sort of commutative graph homology, in particular of the flavor that we've seen already yesterday and today. So for example, it can compute this Grothendieck Teichmüller-Lie algebra after results of Willwacher, or top graded piece of the cohomology of MGN after results of Chan-Glacius and Payne. But its input will be Lie graph homology. So in particular, our graphs will be labeled by Lie graph homology classes. Okay, and I say new here, but really the only thing that's really new is sort of, I would say, is the differential. The rest of these aspects will have a flavor that's probably familiar to many of you. And if you're familiar with this language of modular operads and the Feynman transform, will be very familiar. Okay, but let's try to do these four things first. So what type of graphs do we consider? And here's a picture. So our graphs have, well, edges, of course. You see we allow parallel edges and loops. Parallel edges and loops, or maybe tadpoles, call those. They have legs, so sort of like edges, but they are only adjacent to one vertex at one point. And you see here two different types of vertices. So I've drawn them in red and gray. So the red ones here and the gray ones here. And I picked those colors because somehow the red ones are like the heart of the matter and the gray ones are sort of boring. That's the idea. And then we also have some stipulations. So this graph is allowed because it doesn't violate any of the following conditions. So, or it adheres to all the following conditions. So the gray vertices have to be stable. That means there's at least 3 incident edges or legs. The red vertices don't need to be stable. There's no parallel edges that run between gray vertices. So here I allow these parallel edges because one of the adjacent vertices isn't gray. And there's no loops or tadpoles at gray vertices either, but we allow tadpoles at red ones. And the number of red vertices is not 0. So the number of gray vertices could be 0, but red vertices have to be there. And finally, the graph should be connected. So this is the type of graph that we consider. Of course, please feel free to interrupt me with questions anytime. And then we'll put some labelings on this graph. So the first thing is a genus, which will label the red vertices. And the genus is just that's just a name. So it's a positive integer associated to each red vertex. And I want to emphasize the word positive here, so we don't allow genus 0 labels. And also we label the legs, say bijectively 1 through n, for the appropriate n. So I've done here, but I'll often, let's say in pictures, just suppress the labeling. So it's always there in the background, but might not see it. Okay, so that's item 1. What type of graph do we consider? So what do we associate to each such graph? Well, consider that next. And yeah, okay, to do that, I need to recall some work of Connaught, Kasabov, Hatcher, and Votman. So let me define first this space, xgn. So it's just a a wedge of G circles and n-pointed intervals. So this is the case where G is 3 and n is 3, pictured here. And the endpoints of these intervals I can distinguish, so they're labeled. And let me define a group which looks at boundary preserving self-homotopy equivalences of this space, and then takes homotopy classes of those. So that's a group, and okay, maybe it's rather mysterious at first, but so Kannert, Kasabov, Hetcher, Votman tell us a few things about it, and well, they tell us a lot about it maybe, but I'll just say a few things that I need. One is they tell us where the group homology is supported. So I'm doing everything with sort of trivial or rational coefficients, let's say, in this discussion. And I'll mostly be concerned with just reduced homology. So there's only a range where it can exist. Let me call this top dimensional possible homology the virtual cohomological dimension, or VCD. They also tell us in genus 1, so just one circle or one loop, that as an SN module, so the SN action permutes these boundary points essentially, that it's irreducible in each degree. So irreducible is an SN module. And well, it's okay, if I, the homological degree is odd, then it's just 0. But if it's even, and you look at the VCD, which in this case, so if I had 2G was my I, then I think that VCD would be at G equals 1. So it'd be 2J plus 1 is N. We just get a copy of the alternating representation. It's trivial if I look at genus 0. And yeah, one more thing maybe I'll use. This collection of all these homology groups as graded vector spaces, so with rational coefficients, it forms a modular operad, which means there's some sort of coherent gluing along graphs of these homology classes. Okay, so that's just a quick recollection of a few facts that I'll need, and then I'll go back to the question, which was, what do I associate to each of my graphs? So what I'd like to associate to each of my graphs is a graded vector space. So my graph is gamma. And what I do is I look at just the red vertices, and I'll label that with the appropriate homology group or say appropriate graded vector space of the reduced homology, where G is the label of the red vertex and N is the number of adjacent half edges, so edges and adjacent edges and legs. So in this example, I just take this, H gamma 2,4 and gamma 3,6, and I would tensor those two graded vector spaces together. Okay, this is a slight oversimplification because, I mean, one small detail is what I'd really like to think is that I have an identification of this 4 endpoints with the adjacent endpoints here, or adjacent half edges. So it won't hurt to just think that I've chosen a labeling of the adjacent half edges by 1 through n. So 1 through 4, 1 through 6 here. Maybe I'd like to actually do it in a more coordinate free way, but for the purposes of just thinking about it. What that means is if I permute, say, edges in a graph, it can also act on a vertex by using the SN action. Another thing, of course, is I want to make the edges odd, or maybe I shouldn't say of course, but I do want to make the edges odd. So formally how I would do that is, let's say, take the set of edges, take the vector space generated by that, take its exterior algebra, and then look at the top exterior power. So this has the effect both of shifting the degree of everything up by the number of edges and giving the edges in order. But if I permute, then I just get the sign of the permutation. Okay, well, I'll just suppress those technical details and you can think it's just the tensor over the red vertices of these reduced homology groups. Okay, so just a few things about this space L gamma. So it's itself a graded SN module because I can permute the numbering of all these legs. So this would be like an S5 module in this case. the degree of an element, because of this top exterior power of the set of edges, it's the number of edges plus the homological degree. So it's sort of bigraded, but I'll take the total grading. And it has an action of the automorphism group of the graph. And that acts sort of diagonally, or acts both on the edges and the vertex labels. So for example, if I exchange these two edges, that's an automorphism. That would produce a -1 because it's an odd permutation of the set of edges, but it also acts on this by permuting the two adjacent edges. So sort of the S4 restricted to S2 action. And if that action was trivial, then the whole element would have to vanish in the co-invariance by the automorphism group. But in general, that need not happen. It depends on the SN representation type. Let me call it, okay, a graph is type GN. If it has total genus G, that means the Betti number plus all the red vertex labels and N legs. And I sort of already gave it away that I want to mod out by the automorphism group of the graph. Look at all graphs of type GN, and I'll call that so LGN, I guess. So this is the graded vector space that I want to make into a chain complex, the sum over all graphs of that type.
Ben, sorry, can I ask a question?
Yes.
Sorry, I should have asked this earlier. So this homology of these gamma GNs, I just not very familiar with these. What is like a typical example of, or how should I think of these homology classes?
Yeah, so I think one thing you could start with in genus 1 is you could think about the homology class which sort of wraps around the circle, and that's somehow going to generate everything. Then I think, so what do I mean by generate everything? So it's a modular operad, so you can compose. So you can think of so for example, suppose I look at the case where the first non-trivial homology class in genus 1, that would occur when n equals 3. So I wrap one interval around. That's going to be a homology class of degree 2. And then I could start composing up with trivial things, and that should in some sense generate every homology class of degree 2. And I mean, the fact that all of these as SN representations are irreducible means that if I have an operation which is non-trivial, then it somehow has to generate everything if I take the SN span of that.
Yeah. Is there a relation to the out of N story?
Well, yeah, okay, that's also a good point. So I'm talking about sort of low genus and then going up in N. But what you could also say is N equals 0 and going up in G. And in that case, it's exactly the homology of out FG. So, I mean, that was the original sort of motivation for this work, is that you want to look at homology classes of out FG. And so you say, well, okay, we can compose along graphs these maybe simpler homology classes of gamma 1n or gamma 2n, things like that. So yeah, you can certainly think of it as a homology of out FG if you take n equals 0. Yeah.
Thank you. That was very helpful. Thanks.
Okay. Okay, so we'll look at these labeled graphs labeled by these homology classes. I mean, you can see it in this story, though, like I always, because they label a graph, I essentially always have legs. So I'm sort of like maybe more inclined to look at the case where G is low and N is high. So let me tell you what the differential is. Yeah. As the following form. So starting from a homogeneous element, like that means that I have a particular I and J homology classes labeling these two guys. Let me pick a connected subgraph. let me contract it, which means essentially erase it, and then replace it with a vertex, which keeps track of the total genus. So here we had genus 2, but then we also contracted a graph whose Betti number was 1, so it's 3. So this should index a term in the differential, or I would like it to, but there's some missing information here, which is that these red vertices all have to carry homology classes. So I'd have to tell you what homology class goes here. That's some sort of higher composition operation than I need to define for you, right? I started out with a homology class labeling this guy here, which was genus 2, n equals 4. And now I somehow need to end up with a class genus 3, n equals 5. How do I do that? Well, okay, let's first appreciate that we know how to sometimes do it. So I've told you that the homology of these gammas forms a modular operad. So that means there are some operations which contract edges. So for example, I know how to contract this like a single edge here, a single loop. That's defined for me in advance. And I could also contract an edge like this because these gray vertices they're not labeled, they don't do anything. So I could just contract it, that's fine. An edge like this, I could easily contract by saying, well, I'll consider these homologies as something like a module over the commutative operad, which is the same as saying, I pretend that this is labeled by the class of genus 0, the H0 genus 0. So it's not hard to contract a single edge. And these operations would have degree -1 because they lose one edge and edges have degree 1. So those are all examples of what I was talking about in the previous slide, and they would give you terms in the differential. But what if we have a subgraph with more than one edge? So that's why I say higher composition operations, because the degree, so like this example I had before, it would have to go to sort of like, okay, L gamma prime, right? Gamma prime is just this graph. Well, there's only one red vertex in this example. So it'd like have to go to this H24 to H35, but the degree would have to be, okay, homological degree E -1. So the degree of the operation would have to be the number of, if I want the total degree to be -1, the degree of the operation would have to be E -1. In this case, it'd have to be 2. So the word higher here could be just interpreted as saying raises the degree. So what would these operations be? I mean, well, let me make a definition. Let's say that a collection of chain complexes, some AGN, that has an operation like the one I sort of just described with that degree for every such graph, gamma. Let me call that an A infinity modular operad. And we use this terminology in sort of to make an analogy between associative algebras and the process of resolving those to get A infinity algebras. And modular operads and sort of resolving those to get A infinity modular operads. So the way this analogy sort of goes is you think of in an associative algebra, you can multiply 10 things together, but only sort of 2 at a time. Now the order doesn't matter, order of a parenthesization doesn't matter. Or maybe I should say the parenthesization doesn't matter, but you can only multiply things 2 at a time. Similarly, with a modular operad, you can compose along any graph, but you sort of have to do it one edge at a time. And then you say the order didn't matter. On the other hand, in an A infinity algebra, there's a mu n. So a way to multiply n things together, which is a generating operation. It can't be decomposed into smaller operations. And likewise, with an A infinity modular opera, there's an n-1 edged composition, but it's a generating operation. It can't be decomposed into just doing one edge at a time. Okay, so let me call these sort of mu n's. I'll use the terminology Massey product. And I'll revisit this analogy, yeah, okay, if there's time. So with that, at least I've rephrased the problem. I wanted to define this differential on LGN, which depended on sort of contracting graphs. And now at least what I can say is that if I can endow this collection of graphs, so this means over all GN, collection of graded vector spaces, with the structure of A infinity modular operad, then I'll know how to do that. Okay, so it's just sort of rephrasing the problem. But okay, so here's, let me say I can do that. So the collection of these graded vector spaces carries the structure of an A infinity modular operad. That in and of itself would not be interesting because I could just, for example, pick everything to be 0. It should have some property, well, or hopefully some sort of interesting property, which makes it a structure worth considering. So the property then is that there exists a short exact sequence of the following form. So on the right-hand side, we have the complex that you get out from these operations, except for I've taken its linear dual, which is sort of a choice. On the left-hand side, you have the graph complex GC2, looking only at genus G. So this is Will Walker's notation. So also sort of the commutative, K-twisted variant of commutative graph complex in the sort of Feynman transform terminology. And in between, there's some acyclic complex. Okay. This is just the case where n equals 0. We'll also look maybe at the case where n is not 0 later. So that sort of tells you the differential relative to some things which I've sort of not described very explicitly, but just claimed they exist. But it also tells you sort of what it computes, right? If not why, because if I look at the short exact sequence, I know that the homology of the right-hand side and the homology of the left-hand side have to be the same in the long exact sequence, just because I'll get zeros for this middle term everywhere. So for example, it would tell us that if I take the homology of this guy with appropriate degree shifts, I would get this Grothendieck-Teichmüller Lie algebra just applying Will-Walker's result. So let me tell you, what is this acyclic complex? So formally, if it sits in a short exact sequence like this, formally it has to look sort of like this. I have to be able to express things in the middle as something on the right plus something on the left. So what's on the left, this GC2, is just the exact type of graphs I was considering if they had no red vertices, right? The stability condition, connectivity condition, no tadpoles and bonding out by automorphisms, all the same conditions that you would find here, if you're familiar with it, or can take it as a definition if you're not. So just for getting the differential, this acyclic complex sort of has to look like this, but of course it can't split. There's a lot of homology here. There has to be a differential connecting these two pieces. Now, if I write it with a linear dual here, I'm no longer contracting subgraphs, I'm expanding them. So I could consider it with the expansion differential, and then it goes from sort of the right-hand side to the left, or the contraction differential left to the right. Okay, so I mean, formally it must look like this, but the question then, of course, is like, what does this D like really look like? So let me give you an example of this D. So we've seen this these pictures before, of course. So using this correspondence with the Grothendieck-Teichmüller Lie algebra, we have a family of non-trivial commutative graph homology classes. So I'll call them sigma 2j plus 1. And these are just their leading terms, the wheel graphs. Okay, so picture them this way. But let's also recall from this slide that the genus 1 homology here of this gamma 1n, or gamma 1 2j plus 1, is the alternating representation in the virtual cohomological dimension in the odd case. So I can fix a generator, just a single non-zero, any non-zero element, which would generate this homology group. Okay, and I'd like to claim that these classes are related by the connecting homomorphism of the associated long exact sequence. Well, you see, I mean, formally they're indexed the same way, but this has genus 1 and this has high genus 2G plus 1. So I have to say what precisely is the relation. Okay, so first I needed a calculation. So this class alpha 2J plus 1, it's the image of the Massey product. So remember, that's this operation of contracting a graph associated to a stable 2J plus 1 gon. So let me see what I mean by that. And then we can just look at the case J equals 3 for example. Stable 2J plus 1 gon means that you take a polygon and you just put a leg at each vertex to make it stable. Okay. There should be an operation which contracts all 7 of these edges, and that should land in degree 7 minus 1, which is 6. So I've described for you, or at least told you, that there exists this class alpha 2J plus 1 here. So it makes sense to say that this guy, which is just sort of the ground field, which is just Q, sends 1 to this class alpha 2J plus 1 in H6. So that's a calculation. Well, actually, it's a little bit misleading to say, I mean, because I fixed the generator alpha 2J plus 1, but really what I should have done is I should have proven that this is non-zero and then called that the generator, but okay. And this is the calculation. So how will we use this one sort of Massey product that I can calculate, or that I've calculated so far, to detect the wheel graph, which after all has n equals 0? Well, okay, here's the wheel graph, and there's a sort of, I think, obvious first guess, which is that you could take the exterior polygon, the exterior 7 gon, and you could contract it. And that would give you an element in this class, in this complex L that I've been talking about. It would have 2J plus 1 as its genus, and it would have n equals 0. The problem with this, if I look at the expansion differential, for example, and I apply it here, then I'll get the wheel graph, so that's fine. But if I apply it here, I'll get a bunch of other stuff. And so that makes it hard to conclude that the wheel graph would be a boundary, or it would be the image of this D. Well, I mean, in fact, it wouldn't be the image of this D on the nose. So that doesn't work, actually. So okay, let's go back and try again and stare at this for a little bit longer. And then we see a 7 gon sitting inside like this, or the choice of 1. And if I contract that graph, I get this, right? Because I've got these 4 spokes that are not red. So those are going to get turned into tadpoles when I contract, because they run from the red to the red. And then I've got a single vertex which is not getting hit by the red, and that's going to be left alone as a gray vertex. 3 parallel edges running between the 2. Okay, so this avoids that problem that now there's no expansions at this differential. So there's only expansions at this differential. So we could hope that maybe if I take D of this element in this class, I get the wheel graph. But of course, there's the same issue as before, right? I need to say what labels this vertex here. So let me define an element like this. This needs to be labeled with a class in H6 of gamma 111. Okay. I know how to find a class in H6. That's this alternating class, but it only has 7 inputs or outputs. So what I'll do is I'll compose with a copy of the commutative product, or a gray vertex, for each tadpole. And I do that, it gets up to 11. So that's good, right? The result is where we need it to be. But this space, so it has dimension 1260. So you might think, well, I've made a relatively arbitrary choice of an element that's going to go here. But in fact, that's not the case. If I mod out by the group of group of automorphisms of this graph, right? So this has an S11 action. The automorphisms of this graph is a subgroup of S11. So I can mod out by that and take the restriction. The result is only one dimensional. So that's the first result. So that's just a calculation of representation theory. And this class will actually span it. So this class is non-zero when passing to the covariance. And that works for all J. So what I'm really saying here, I mean, this is a statement about just group theory. So the automorphism group of this graph, I can permute these three guys here. I can permute the four tadpoles, and I can switch the tadpole, the two legs in the tadpole, or the two flags in the tadpole. So that's where I get the automorphism group. It's S3 cross product of S2 with S4. So the S4 is the tadpoles, the S2 is the flipping, the S3 is these three edges. That sits inside S11, it's a subgroup. So then I can take the restriction of the calculation of Konotka, Sabov, Hatcher, and Votman of what this group is as an S11 representation. And I can ask for how many copies are there where, okay, the signs are determined what they have to be if it's going to be non-vanishing. They have to be minus signs here so it doesn't vanish. There have to be minus signs switching the edges, and it has to be a plus sign when I switch the order of the loop. How many copies of that irreducible, one-dimensional irreducible are there? The answer is always one, and that works for all J. Okay, so with that sort of group theory computation, we have the following result. So if I take this element and I apply that D from before, I get exactly this sigma 2J plus 1. Or equivalently, if I look at the linear duals of all of these complexes, I can use the contraction differential. Then the wheel graph is not a boundary. So the wheel graph with contraction differential is definitely a cycle, because if I contract any edge, I get parallel edges. So this says that it's not a boundary, so therefore represents a non-trivial class. And yeah, I mean, of course, this result is known. I mean, we heard about it yesterday even, but the important point I want to emphasize here is that I didn't have to import any information from the growth and detectability group. It's just a sort of combinatorial or sort of group theoretic proof. Okay, and let me hit escape here so that I can check the time. So I have a little bit of time left, yes. Okay. So let me now look at the case n equals 0. N is not 0. So it's, sorry, so we were looking at the case of n equals 0 before, but this will work for n not 0 as well. So yeah, I mean, let me maybe throw out the case where G and N are both 1. And I can say there's the same sort of short exact sequence that we had before, except for now I'll look at sort of the n-pointed graph complex, so it has n-ordered legs. And otherwise, everything sort of works exactly the same. And again, using the long exact sequence and homology, we can conclude that these two have the same homology modulo some degree shifts. And it turns out that the degrees work out such that it actually, I mean, the degrees match here computes this reduced homology of the tropical moduli space of curves. And so SN equivariantly. Or equivalently, it computes the homology of the Feynman transform of the modular envelope of the commutative operad, or equivalently commutative graph homology with odd edges. Okay, so let's say if we can say anything like, or you know, how are the features of the Lie graph homology reflected in this computation or in this isomorphism? And yeah, so I really have to look at the case of low genus to be able to say anything concrete. So let's say genus 1. So what am I looking at now? I'm looking at L1n. So that means I have these types of graphs as before, but their total genus has to be 1. But they always have to have then exactly 1 red vertex, because if they had no red vertices, they'd be genus, they would be disallowed. And the genus of these has to be positive. So there's at most, both at most one and at least one red vertex. So exactly one red vertex. And then the rest of the graph has to be just a tree because the total genus has to be one. So I have to have one plus the Betti number equals one. And this one, this distinguished vertex, is labeled with a homology class, which is necessarily even by the result I gave you earlier. Okay, and the internal degree can't decrease if I'm looking at contraction differential, because it can stay the same or it can go up. So there's a nice filtration here to study this complex. So I'll label the, I'll erase the genus label because it's always one now and just put the degree label in green. And yeah, let's just, to be concrete, I mean, look at the case n equals 5. So for the case n equals 5, the maximum valence is 5. So that tells me that I can have these possible red vertices, they have degree 2 or 4 only. In total degree 2, I would have to have, let's say, an H2 with no edges. Let me just look at the case where the internal degree is 2, right? We have that filtration. Total degree 3, I could have one edge or I could have 2 edges, so total degree 4. So here's internal degree 2 complex, just drawn in sort of cartoon form with contraction differential, which goes this way. And then I could also have my internal degree 4 complex, but the only thing I can have there is just the corolla. So if I line this up, the degrees go like this. And these are all one-edge contractions with this horizontal differential. Now, potentially I could have higher operations, but those would have to run between the rows. And just for degree reasons here, no higher differentials can exist. So the complex is really just this. And so what you can show about this, just sort of working in a hands-on way, the homology of these rows is concentrated in the leftmost degree, so having the most edges. In particular, the homology is all concentrated in one total degree. And the ranks of these rows, homology groups, are given by Stirling numbers, which, recall, counts the number of even permutations with a fixed number of cycles. And that number of cycles always has to be even because the homology class is always even. So in other words, the total homology is just the number of even permutations of, in this case, 5 minus 1 is 4 of S4. So that's, I mean, that's consistent with a known computation of Chan-Glacius and Payne, but just a different sort of way to do it. What's even easier is to look at the, let's say, the anti-invariants. So that was SN equivariantly, although I didn't tell you anything about the SN action here, because it's sort of somehow weirdly mysterious how it's compatible with the SN action. I mean, this, okay, the SN action decomposes over these Stirling numbers, but not in any way that sort of appears to be nice. So let me just go to the anti-invariants. So what do I mean by that? I mean, tensor with the sign representation and take the invariance of that, or in other words, take just the number of copies of the alternating representation in each of these SN modules. If I do that, then this complex becomes extremely simple because every time I have a commutative label, this has to have a trivial S2 representation, but it also has to give me a minus sign. So every time I see this, it just vanishes. So that would be 0, that would be 0. And this guy vanishes because I know its representation type is not alternating. And all I'm left with in the case of the n equals 5 anti-invariants is just this class. Or in general, all I'm left with are the classes I've already told you about. So another way to say that is that, yeah, these classes I already told you about. Another way to say that is that the anti-invariants of these two objects happen to be the same, right? Because this computes the anti-invariants of this one. But on the other hand, the only anti-invariants that I have sitting around are the corollas, which are these ones. So that's for genus 1. Maybe That may say something about genus 2. So in genus 2, now remember in genus 1 you had one type of element is just a tree with a distinguished vertex. In genus 2 you have three types of elements because you could have a tree with two genus 1 vertices. You could have a tree with a genus 2 vertex, or you could have a graph whose Betti number is 1, but whose genus labels add to 1. And that means in particular, there's one with genus 1. Okay, these three types of elements. The homology necessarily has to be supported on the subspace with one red vertex. Okay. But maybe, yeah, okay, maybe I don't want to say, it's sort of hard to work with directly. Like these interact in sort of more complicated ways. There's not necessarily a immediate filtration to work with. In particular, if I look at contraction differential, I could contract this to get this. I can contract this to get this, or I can contract this to get this. Okay. So let me again just pass the anti-invariants to simplify the story. So now I'll look L2n, but the copies of the alternating representation living everywhere. So again, the gray vertices can have at most one leg because they'll vanish. The S2 representation action here is trivial. So they'll vanish if they have two or more legs. So these actually just all become 0. So that's sort of nice. But there are still non-zero elements of all these three types. There's, for example, things that look like this. And let me call this P35. So what is it? Or let's say PRS. It's a R plus 1 gon labeled in genus 1 with this class alpha S, which I've told you about. You notice that each of these are stable, but they only have one leg. In this complex, the role of these trees here, which just have two genus 1 vertices, we'll be able to see equates in homology PRS with PSR. So those are actually homologous cycles in the homology. And then what about this? We have only correllas with a genus 2 vertex, because if I have a genus 2 vertex, then it has to be a tree again. So I just have the correllas as before. So we know this is something like the homology of gamma 2n, but the anti-invariant part, what role is this going to play in the homology? Now, let me just tell you the computation. So I'll tell it to you for the case when n is even. The anti-invariance here, it's quasi-isomorphic to the following complex. So I take the span of these PRS guys, which I had before. So it's something like a polygon, but now one of its vertices is distinguished and labeled with a class we know. R and S should both be odd for it to be non-zero. And then I'll look at a differential which maps to this corolla. So it's the contraction differential of contracting that polygon. The first thing I'm saying is that it's surjective. And in particular, what that means is that the number of alternating classes in delta 2n, which is the homology of this complex, has to be equal to the number of things in here, which I can count, is just the floor of n minus 2 over 4, minus the dimension of this thing, if I knew what that was. So now if I know one of these two things, it tells me the other one. That's the first observation. Well, okay, I know the right-hand side by this work of Konotecher, Kasabov, and Boatman, which I've mentioned before and will mention again. And they compute that this is equal to the space of modular cusp forms, n minus 2 over 4, n minus 6 over, so n minus 2 over 4 minus n over 6, the floor of each of those is a explicit formula for that. And so I find that the dimension of, or the number of copies of the alternating representation in delta 2n is this. And now, of course, you could simplify this expression and just call this the floor of n over 6. But I keep it in this form because it's something like generators and relations, as is also depicted here, generators and relations. And what do I mean by that? So remember above, we had this class sigma 2j plus 1. It was somehow detected by Lie graph homology classes that were of genus 1. So a very naive question I could pose is, are these guys, the Lie bracket of 2 of them, is that detected in genus 2? Well, in some sense, the answer is yes. So let's consider now this growth and detectmiller Lie algebra with its depth filtration. And we have the following consequence of the calculation above. So I take my element PRS, so it's a polygon with a distinguished vertex, and this special genus 1 class is this label. And I view that as an element in L2n. It's anti-invariant. And I'd like to map that to the Lie bracket of 2 of these guys with Lie bracketed together of the appropriate R and S. Now remember, I told you that PRS was homologous to PSR. So in homology, the order here doesn't matter. But right here, I have R less than S, just for convention. Okay, so that lives in depth 2. I can mod out by depth 3. And if I do that, it induces an isomorphism. That's sort of an immediate corollary of the above computation. And the reason for that is because we know sort of the relations between bracketings modulo depth 3. Those are classified by Schneps and showed to also be in correspondence with modular cusp forms. Okay, so this isomorphism just realizes those relations as being homology classes in gamma 2n, anti-invariant. Yeah, okay. So, I mean, the sort of slogan here, I guess, then is that to understand the depth 2 part, we had to understand Lie graph homology only up to genus 2. And you could ask, does this pattern continue? By which I mean, would genus 3 tell us something about depth 3 and so on? And I don't want to claim that it does. I mean, there's clearly some relation, but I don't, checking my time again. So I don't maybe have anything more to say about that than this. This does give us some idea about, I mean, this guy formally has to have the structure of a L infinity algebra, whose homology will give us the Lie structure here. And this tells us a little bit about what it looks like, but only sort of modulo higher depth. Okay, so there's more computations you could do or more fun you can have. I think I have about 10 minutes left or so. So what I'd like to do in that time is maybe tell you sort of why this works. I mean, I just asserted that there are these structures that have these properties, but why does it work? Okay, so by why does this work, I guess what I mean is why should there be a way to glue these 2 complexes together in some sort of acyclic fashion? So why is the complex acyclic? And it has to deal with our analogy that we mentioned before, that an A infinity modular operad behaves sort of like an A infinity algebra. And A infinity algebras have a nice property of homotopy invariants. So the same thing should be true here if I extend this analogy. And yeah, that's called the homotopy transfer theorem. So let me give you a generalization of this classical A infinity story to modular operads. And that is that every DG modular operad is quasi-isomorphic to some structure on its homology. And that structure is that of an A infinity modular operad. So let me say how we can then use this to construct the acyclic complex from the previous slides. So this modular operad here, it's the homology of a modular operad. So therefore, I can use this homotopy transfer theorem to put higher operations on it such that these 2 guys are equivalent. Now, what is this FT here? So that's, I write that for the Feynman transform, so as defined by Gessler and Kapranoff. And so the Feynman transform allows us to describe graph homology theories. But what's also very important is that Feynman transform has nice homotopical properties. Namely, if I do it twice, I get back to where I started. So let's use that. But first I need to first I need to generalize it to A infinity world because that's where I'm living now, but that can be done. And I'm going to write it as lowercase to indicate that I've sort of changed it, but okay. In principle, it's the same. If I do it twice, I get back to where I started. So I take it here and I'm doing it twice on the right-hand side, but it preserves weak equivalences. So what I get on the left-hand side is still equivalent to it. So this guy is equivalent then to this Lie operad as input. But the Lie operad, viewed as a modular operad, it's just 0 in higher genus. It's just an operad. So that means that this guy has homology equal to 0 in higher genus as well. And so this is the complex that I'm using in the, oh, this should be lowercase, I guess. This is the complex that I'm using in the previous slides. It's an acyclic complex that has these two pieces glued together. And sort of formally, you can conclude it's acyclic. Doing the computations can be maybe as hard as you like. Okay, well, yeah. I say it's the complex is from the previous slides. That's not quite true. It's true up to some contractible complexes. So you can sort of mirror some of these contractibility results. In particular, contractibility of tadpoles and higher genus vertices and things like that. You could mirror that on the other side, and then, it makes the computations easier. So up to some contractible complexes, it's this. Well, okay, maybe I have time to peel back one more layer. Why does the homotopy transfer theorem hold? Like I just told you that we do our computations using this homotopy transfer theorem. Why does this hold? Classically, the story is, okay, homotopy transfer theorem, it's because the associative operad is causal, so associativity has some nice property. Well, why does that hold? It's because these associahedra, which you can get by writing down all possible ways to associate elements, are contractible. So, classically, the story, why does the homotopy transfer theorem hold, roughly can be reduced to the phrase that associahedra are polytopes. That's why. So let me show you that there's some polytopes sort of under the hood here as well. First, maybe I should recall associahedra. And I'll do this very, very quickly. Here I have 4 letters, A, B, C, and D. Here's a way to parenthesize those 4 letters. Let that correspond to a vertex in a polytope on the right-hand side. Now let me erase one pair of parentheses and let that correspond to an adjacent edge. Or I could have erased the other one that will correspond to an adjacent edge. Now I can reparenthesize it and erase, reparenthesize and erase, reparenthesize and erase, and I get a pentagon. I could also consider this string having removed 2 pair of parentheses and call that a 2 cell. So the sort of the standard construction of associahedra is we look at all ways to parenthesize elements. Okay, so let's generalize that or draw an analogy to our current context. So associativity, instead of drawing it as ABCD, let me put it as vertices ABCD in a graph. This is a particularly simple graph. Then parentheses should correspond to some sort of nested subgraphs. I'll call those brackets. And it's important that the brackets, they're either nested or disjoint. And if you do this, then you can prove that any space of the space of bracketings of any graph is contractible, is a polytope. It doesn't have to be a graph of vertices arranged in a line like this. For example, you could have something like this, and you fully bracket it, that's a vertex, but then you just forget and think about other ways to bracket and use the same adjacency relations, and you'll get a polytope there as well. The degree of this polytope is the number of edges minus 1, just like the differential in our, or the degree of our operations. That's not a coincidence. For example, yeah, I don't know, maybe call these bracketahedra. The icosahedron corresponds to this graph, the cyclohedron, the permutahedron, and actually there's two more, and these are the only ones in 3 dimensions. So these are 4 edges, so a 3-dimensional polytope. Here I've drawn like if you removed one face and you just like flattened it out, that's what this picture is supposed to be. And this one I couldn't find a name for it anywhere. These aren't the only graphs with 4 edges, but all of the polytopes that you get associated modular operads look like this. And these are just, they have cells corresponding to all ways to look at nested subgraphs, or all ways to sort of partially compose within a modular operad. That's a polytope, and that tells you immediately that the operad, which encodes modular operads, is a Koszul operad. You can prove that. Yeah, I mean, there's maybe, I mean, now we're sort of peeling back more and more layers. There's one sort of issue. Okay, you can't encode modular operads with a quadratic presentation, which you need to prove causality if you just use a classical colored operad. So you need to do something a little bit more involved. And so my first, when I proved this originally, I used sort of groupoid colored operads, so I had to develop causal duality theory for that. But there's another thing, sort of more or less equivalent thing you can do, and that's use this notion of Feynman categories Ralph and I worked on. And actually, it turns out, so there's recent work, I mean, the adjective that you need to say which sort of operads like this or generalized operads are causal was already sort of there in the paper. And so we recently extended this beyond modular operads to sort of any Feynman category of graphs, roughly. So you could now play these same games with directed or multi-directed graph complexes. Okay, I can't see the clock, but I promise this is the last slide. Yeah, I mean, maybe I should say, sorry?
It's perfectly timed.
Oh, good. Yes. Okay. First time for everything. Yeah. I should say also, I mean, Ralph, I should plug Ralph's talk later this week. Maybe we'll talk a little bit more about this. And then, yeah, so this is the last slide. The bigger picture somehow is that causal duality theory for operads in the appropriate sort of derived setting builds a bridge between causal dual graph homology theories, and in particular between sort of what I showed you here, like Lie graph homology and sort of untwisted, or a commutative graph homology and it's twisted. So there's always this parity sort of change, whereby every time you sort of prove something new on one side, you can ask, what are the implications on the other side? Or can I see it on the other side? And that may be hard computation, but at least that question is well defined. Now, there's nothing special about commutative and Lie here, other than they're the most interesting, perhaps, example. But we could also look at, well, for example, I could look at commutative as input and Lie as output. That would be valid. Or I could look at the associative operad and ribbon graph complexes as possible another input. I could also look at, say, the modular operad of the open moduli space MGN. So it's K-twisted modular operad. And it's not formal as a modular operad. So what's definitely not true is this statement. If you just take its modular operad structure, but with higher operations, its Feynman transform will be a model for the Deligne-Mumford compactification in the same way that, well, this is formal. So in the same way that the Feynman transform of this is a model for the open moduli space without higher operations. Okay, but that's really all I had to say, I think. So yeah, here's a brief bibliography, and yeah, thank you very much.
Thank you. So please, questions and remarks. Clap, clap, clap. Francis?
How did you guess I had a question? Yes, thanks a lot. That was really fascinating. And I was trying to take notes frantically, and I probably didn't understand a lot of stuff. But you had this amazing result where you related the wheels to these alpha classes in genus 1. And I was wondering, is anything possible for these classes PRS in genus 2 that you constructed? can you, is there hope to interpret these PRS elements as something in the comodular graph complex? And optimistically, can one see this weight 12, this first relation in weight 12 coming from a cusp form in the homology of the graph complex anyway?
Yeah, I mean, what one wants to do is to take a correlate, like a gray vertex, and to glue it in, so with the right number of legs or whatever, and glue it in, and that would work to construct an element because we're looking at anti-invariants. So all of these legs are odd. So that's no problem in terms of a construction, but it doesn't quite work to give a cycle then, because you have this genus 12 or whatever, I mean, the R plus S something. So it's sort of the wrong thing. It's only the right thing in the associated graded somehow. It's sort of the wrong thing. And it's exactly the same problem that occurred up here, whereby, well, not too many slides, okay, but whereby the parallel edges was the wrong thing because of this high. So it was some work to sort of go from this one to this one. And then the same thing in theory has to be done in genus 2. And I don't know how to do that.
Great, thank you.
Any further questions or remarks, please?
Yes, can I ask a question?
Sure.
Great. So my question is, so you related these classes in this gamma GN complex and decorated your graphs with them. Can you also do the opposite and take the classes in, say, this GC2 graph complex and decorate a graph or the vertices of a graph with them? Because there's this forested graph complex that computes exactly this gamma, the homology of gamma GN. So dually, one might also be able to think about this in this sense, or not. That's a question.
Yes, I mean, well, I can say one thing I know that you can do, which is that you could take the homology of the commutative graph complex, or equivalently like the homology of delta GN, and use that as your labels now instead of the gamma GN. And that would be acyclic, and then you could get this, you could get this piece out of there. So you would, once you sort of take the quotient, then you know you have a complex that computes the gamma GNs. Okay, so I know you can do that. It's a little bit harder because you don't have this filtration by internal degree, because the edges are no longer degree 1. So there's, so I have looked at that, but I just haven't been able to, let's say, make as much progress. It's a little easier in the sense that, at least as a semi-classical modular operads, the delta GNs are formal. So you would be able to know formally that there's no higher operations up into a certain point. Yeah, I mean, so the answer, of course, is yes, you can look at it, and there's no, I mean, it gets very complex very fast. So one sort of has to know what one is looking for, and then maybe you can find it in that model.
I see. Yeah, it's just because also in this GC2 complex, there are also, besides the wheels, there are more sporadic classes known. And it would be very interesting to know what they correspond to in the cohomology of this gamma.
Yes.
Yeah, go ahead.
So there's some relation between Cazul duality and Verdier duality. Do you understand that? Can you explain it?
Yeah, I mean, at the categorical level, I think I understand it. I mean, you can think of a modular operad as, or describe it as something like a sheaf on a space of graphs. And you could do the same thing for a cyclic operad. And if you do that, then you can interpret the Feynman transform as the Verdier dual. And what that buys you is this sort of six functor formalism from Verdier duality can be interpreted in the language of the bar constructions for operad-like structures. So in particular, what it tells you is that if you take, so when you form these graph complexes, what you do is you extend a cyclic operad by 0 and then take its dual. But by sort of the 6 operations, and because you're in a particular case where the morphism is, say, proper, the equivalent notion, that's the same as if you had, what did I say? Extended by 0 and took the Feynman transform. That's the same as if you had first taken the bar construction and then of the cyclic operad and then taken the modular envelope. So there's a way to realize the Feynman transform as the derived modular envelope. And that has some sort of maybe nice homotopical implications. I'm not directly using that. I mean, but maybe one thing I can say, though, is like what started all of this thinking in the first place was I didn't understand why people didn't use the nice homotopical properties of the Feynman transform when they studied graph homology. And so now I sort of understand why. It's because it's very, very delicate and complicated, but the Feynman transform does have nice homotopical properties. It's not just that it can describe graph homology classes. That's sort of one maybe philosophy here.
Yeah. Well, this is all this is fascinating. Thank you. Yeah. Maybe you could leave the Zoom on and let people go who want to go and make Ben stay.
This goes to Marco, I guess. He is the host.
Yeah, can do that.
Okay, before that, are there any further questions or remarks?
So then I had a very silly remark, and I'm sorry if you already know this, but these are graph associahedra, right?
Well, yeah, I mean, you can describe it as the graph associahedron of the dual graph. So it's not the graph associahedron directly, which in particular has dimension determined by the number of vertices of the graph, but it's the associahedron of a dual graph. And so what that means in particular is that all of the polytopes which arise in this way are graph associahedra, but not all graph associahedra arise. Only a sort of, if you like, special subclass of them arise.
But what you want is for them to be polyhedra, so that's
yeah, but right. So like if you want to prove that lemma, like they're all of these are polytopes, one proof would be take its dual graph and then identify it as the graph associahedra of the dual graph.
Thanks. Any further question or remark? Don't see or hear anything.
Vincent.
Yeah, go ahead.
Yeah, hi, sorry for asking a second question. This is a very vague question, but just on the off chance. So those of us who've studied the depth graded of GRT a lot, Dirk is one of them who started this off. Something very weird happens in depth 4 that we don't really understand. Is there any chance that you could shed some light on this from your graphical perspective?
Okay, so let's say not right now, but maybe you could refer me to if there's a published or available work, because I haven't read anything about depth 4.
Well, the starting point is that something called the Broadhurst-Kreimer conjecture for multiple zeta values. And the bottom line is that we know that the sigmas form a free Lie algebra. but in the depth graded, they have a relation.
Mhm.
And so that means the depth graded, there's a spectral sequence on the depth filtration that converges to it butts to the homology of the Lie algebra, which is free. And so those relations have to go somewhere. And the thing that compensates those relations are extra generators in depth 4. So for every relation in depth 2, there should be a new element in depth 4 in one-to-one correspondence with the relations. So there should be modular elements in depth 4. And it would be amazing if you had any interpretation of that from your perspective.
Okay, yeah, thank you for that reference. I mean, certainly at the moment I don't, but it's good to know.
Is any other remark? If not, let's thank Ben again.